I should say guten Abend. Is that correct? Thank you. Thank you so much, first for the invitation, and also, for this great opportunity that I can share some of the research. I understand that, this is a very unique, it's a workshop. I think for PhD student, I think my understanding is, based on inspiration and also probably develop collaborations. So in that case, I would like organize my talks in a way that previously I just want to focus on one topic, but since this is a kind of, so quite relaxed, presentation. So I would like to, so review some of the research pillars that carry on in my group in the past 20 years or so. So here, I come from Department of Mechanical Engineering, University of Delaware, also serve as the director for the Center for Fuel Cell Batteries. So my primary research pretty much on nano. So I can see this TACO program include a lot of catalysts, so that and also water splitting. So that's something that I have been doing. So we have quite a line. So the first pillar that I've been doing for the last 30 years or so, pretty much focus on nanomaterials, especially carbon-based nanostructures, carbon nanotube, graphene. And the recent year, collaborator of mine is working on this quite interesting topic on so-called super semiconductor materials that I'm going to give you example. So the second, so I try to use nanomaterials for energy storage application. So one of the focus is on supercapacitor, or sometimes people call electrochemical capacitor or ultra capacitor. So this one, so very recently, I have another piece, try to use this supercapacitor for different very specific application that I'm going to give an example as well. So the third pillar, again, is for energy storage. So based on batteries, lithium-ion batteries, and the lithium metal batteries. So in this category, we pretty much focus on how to, prevent this lithium dendrite formation, by using different strategies. Again, I'm going to give you an example. The next is pretty much aligned with what we have this TACO program that is for the catalytic for water splitting for hydrogen production. Okay. Again, that I'm going to give you as a recent example here. So in fact, I plan to spend a little more time on this very recent research on solar cell. So this work just published, by the end of November last year. So that we have some conclusion, but so I think probably it's better to present and probably get some feedback, maybe some more discussion, so take this advantage. So first, so for this nanomaterials, so a little bit background. That's so we did some nanomaterials patterning. Use some polystyrene sphere type, and make a very nice arrays. And after that, we deposit very thin layer metals. Okay, so typically it's bilayers. So first, for example, like this one, we deposit cobalt and also aluminum. They are metals, right? So that's we did this temperature dependence. So you can see the resistivity as a function of temperature. So you see here that each temperature increase. So initially very low temperature increase up to a certain point. This is pretty much show this metallic behavior, right? And after a certain point, so that this resistivity, drop dramatically. So very fast, even go to, beyond room temperature. So this part is quite normal for almost all the metals, but this part is unusual, okay? So since this resistivity drop is by almost 1 order of magnitude, so we call this a super semiconductor because this shows semiconductor behavior, at the same time show very, very high conductivity. So how high is that? So if you just simply compare with traditional, so silicon materials, it's a typical semiconductor, silicon. If you compare to silicon, if it's intrinsic without any doping, so the conductivity should be, 10 times, 10 orders higher than this, intrinsic silicon. And even we compare to, the heavily doped silicon, we still have, 1,000 times higher conductivity compared to silicon. So this is why that we analog to superconductors. We know that superconductor, if you cooling down to extremely low temperature, so you basically, without any resistance. And here, the behavior is just differently. That with the temperature increase, the resistance decrease, by 1 order of magnitude. So that is we call this super semiconductor. Okay, so this is some features. Metal, single metals become a semiconductor. So this is one. The second, as I said, ultra low resistivity. The third one that's also can be even just holes dominate the conductivity means it's a p-type semiconductor. So we use this one to build quite since it's a semiconductor, we can build the devices. So of course, dial is the simplest one. We built and we show this one here. This work published just 1.5 years ago. And when we use this method here, the only difference, here we use cobalt aluminum, and here we change cobalt with silver. Okay, so we found this dial behavior, of course, and at the same time, this threshold voltage has become very, very small compared to traditional one, like a silicon is 0.6, 0.7 volts. So and here that we got 0.01 volt. So that indication that if you just use very small, voltage, you can turn on, so turn on off. Okay, so this dial. And at the same time, if you look at the breakdown voltage, so up to 10 to the 6 volts per centimeter. So come much higher than silicon, but comparable to some like a high, band gap materials like a silicon carbide. So at the same at least same scale. So this is right now is my main focus. I think we try to build more devices so that with a high energy efficiency, because you just use a very small, teeny tiny amount of power, you can trigger the device function. So this is a new nanostructure-based super semiconductor. The second one is about supercapacitors. Supercapacitors is electrochemical based. Typically, as they are called super just because the capacitance is much higher than traditional dielectric based capacitor, right? So this is, I think, probably is a common knowledge people already know. And here, the new thing we try here is try to use this supercapacitor or carbon-based supercapacitor to be used as a filter capacitor. Okay, so the function of filter capacitor is nothing but just try to, signals, electricity. So from AC, for example, all the AC, electricity transfer in the long distance we use AC, and you need to convert to, DC, but they still have a pulse. So for many applications, electronics, appliance, you have to smooth this, rate, So in this case, you need to apply the filter, based on capacitor. So traditionally, people use, aluminum, electrolytic capacitor. But this capacitor, hold very high, volume. So if you look at any circuit, probably that component is the biggest component in any circuit design right now. So if you try to minimize, electric circuit, and even like, for example, some chips, so you have to minimize, this capacitor. So the reason we try to use a supercapacitor is just because they can provide very high capacitance, so 1,000 times higher than this AEC, aluminum based. So here we basically the innovation part, we use a template, aluminum template. So we build this really three-dimensional interconnected carbon structures. Like for example, here we use a template and we deposit carbon materials inside, holes. So after that, we remove this template. So we end up with this three-dimensional interconnected, horizontal, vertically interconnected, three-dimensional structure. So that can provide very, very high, frequency response, because for AC, so DC conversion, so you have to have a very high, frequency response. So that typically cut at 120 hertz, right? So look at the response, what the capacitance you have. So in this case, since you have this really interconnected, structure based on carbon, we know is a very good conductor. So we can have this, achieve this high capacitance at the same time, very high, frequency response at 120 hertz. So we did a series of experiments. First, just a simple structure, and also we do some surface, modification, roughening the surface, try to increase a surface area, and then you can increase the capacitance. And also here we do the multiple layers, so like Russia's, toys, right? So multiple, toys. So that you have multiple layers here, and also you can increase the density of this structure by tuning this, template. Increase this structure, decrease the diameter, and also distance between these structures. And just recently, that we also applied to make this Wei junction type for three-dimensional structures. So all the papers just published recently. This is for the we call this super capacitor application for filter capacitor. The third part is about the batteries. We know that so try to avoid this disaster. So typically happening in lithium-ion based and probably become pronounced if you try to develop a lithium metal based batteries. So in fact, we first try to understand, so this dendrite formation, this pretty much the primary cause for this, so like short circuit inside batteries. So we try to understand step by step, like a nucleation, and try to avoid this dendrite formation. So we use some polymer so to uniform the nucleation of this lithium ion. So in that case, you try to avoid this, develop eventually such kind of structure that will be dangerous. And also we try to use like a graphene oxide, try to induce or try to guide, these lithium groups on the lithium metal. So in this case, you can see here there's no any such kind of dendrite formation, but a flat surface. Okay, we also use some calculation tools, try to understand what's behind them. Basically, here just a simply comparison, for example, the two columns. On the left side, you see we apply any physical, power structure, and on the right side, you see that so basically the dendrite still free to grow. So we apply same charge discharge rate for both cases. You can see this one, that's you easily see this dendrite grow very easily, develop so larger structures eventually, get the cell filled. And this one that is pretty much surprise the dendrite formation. That our understanding here, just because such kind of the total structure can dramatically decrease this local flux of lithium ion, and also at the same time delayed transfer of lithium ion to the deposition site. So this is what we understand from this, so some probably some mechanism and this mechanism. Okay, this is about the third part about how to dealing with this lithium dendrite formation. The fourth part is about this water splitting. So try to produce hydrogen. And here the idea we apply very simple. So we know that for hydrogen production, of course, these are photo generated. So you have a catalyst, that is your expertise here. Catalysts typically are solid phase, right? So for water splitting, you have to use water, so that typically are liquid phase, right? And the product is hydrogen or oxygen, they are gas. So basically you have three phases, solid, liquid, and gas, right? So here we just simply change one phase, from liquid water to gas water. That's it. Okay, so you can imagine, so that is gas phases. So you can dramatically increase the kinetics. Okay, and of course, it's increase the conversion efficiency. So the idea is very simple. Just change one phase from liquid to gas. Okay. So here we didn't focus on any individual catalyst, but the method itself. So just give me idea example here. So if you use the liquid water, your efficiency here, I should emphasize this is particular based, solution based. So conversion typically low. The highest so far to my knowledge is 5.9%. Okay, it's different from like it's a photovoltaic cell based. So that is you can reach about 30%, but this is not. And you can see that typical one. So here I should emphasize this is based on cobalt oxide. We didn't optimize any catalyst here, just to see that apply liquid water and steam water. So you can see that efficiency increase very large by almost 20% increase of the efficiency. Also not 20%, it's 20 times, sorry, 20 times increase efficiency. So you might think, okay, so you have to translate, transfer the liquid water to, gas water, so that consume additional knowledge, power. So that here we don't really apply additional, energy source, but simply design this conversion device, and everything from solid. So for example, that's we apply wood. Wood you kind of burn on the surface and try to increase light absorption. And at the same time that this wood can float on water surface. And when you shine light, sunshine, basically you kind of photothermal trigger this gas generation. So liquid water to be evaporated. Okay, so this gas water is kind of up through these wood channels, so that interact with catalyst there. So you have both biophases. So this is we call this biphase reaction, only liquid gas phase and the solid phase. Okay, so that's the results compared to any literature, different type of catalyst we use. So this method show the highest hydrogen production. So I think that's in this space we can definitely develop a collaboration. You have expertise in TU Vienna, so you generate or develop a new catalyst that we certainly can try. So based on this method, so very simple setup. Okay, so all that just a pre-program, and this is my focus for today, to try to discuss this power conversion efficiency of the solar cell. So one keywords I should mention, this will be single junction. Okay, so that's we have some result. I think we haven't really totally understand what the basic fundamental science there yet. But I think the results very interesting and also exciting. Let me just give you outline here. So background, how we did experiment, why does you think you can boost this power conversion efficiency. So how many of you work on solar cell or have at least some basic knowledge about solar cell? Just a few? Okay, thank you. So yeah, we know that's the market is huge, right? So that's from International Energy Agency, it summarized the report for 23. So the new installation, just new installation at that year is 375 gigawatts, okay, based on solar cell, and increase annual increase by 30%. So that is, just from the market perspective. And among this, 375 gigawatts, so 90% are silicon-based. Okay, so that you can see the impact if you try to increase, this efficiency based on silicon. And China itself, so have such kind of market is 24 billion US dollars. That's a lot. Okay, so the take-home message is, it's significant impact money there. Okay, so let's try to increase the power conversion efficiency. Probably this NREL, that is National Renewable Energy Lab in the state. They summarize all the benchmarks for all the development efficiency in the past 30 or maybe 40 years. So you can see based on different type of materials, this they show some increase. They show some, like silicon is here, some 1990s, and here this is a 2024. Okay, so the highest silicon-based, I should say, single junction, it's a 27.3%. Okay, and if you look at all the single, junction, here is some high one, just because the multi-junction, solar cell, so that can over 40%. But single junctions, no one can go beyond 30. Okay, so it seems that 30% is kind of a limit. It's really true just because some people already summarize or theoretically gave us some fundamental evidence that you cannot go beyond that. Okay, so here that's so probably you heard this SQ limit, right? This Shockley Quinzier limit. They did some calculation in 1961, published the results, and that based on their calculation, so the single junction efficiency cannot go beyond 33%. Okay, and this limitation is very much accepted by the community. So even after 60 years, so it's still popular and practicable just because no one can really go beyond that. Okay, so this is you can see here 33% at 1.34 electrovolts. Okay, so that is the limitation for this. So how to go over that? Now everyone tried, but nobody's success. Okay, so we assuming that energy, so from solar, this we call this light energy. Okay, so based on this conservation of energy, the transfer mostly, it's a thermal efficiency here. This conversion efficiency primarily dominate. It's why is it so low? I mean, you cannot go beyond 33% just because majority of them, more than 50%, was lost at a form of heat, dissipated heat. Okay, so that so translate the thermal energy. And suppose if you try to decrease the thermal energy part, that probably can increase the electrical energy part. So that is the electricity. People try to use a solar cell to generate electricity. Okay, so this is the ideal case. So if we do this, so but people try, so people try use the temperature regulation method, try to decrease the temperature, because thermal energy kind of decrease. Okay, increase the electricity, but when people go down to up to maybe just 150 Kelvin and to 200 Kelvin, so people stop just because the efficiency not increase but totally decrease. So this is for all. We look at the literature, we found that there's no such kind of thing happen. But we found so if we do go further deep or low temperature, so scenario change. Okay, this is just based on our another piece of research. We found that silicon, if you go down to about 10 Kelvin, that mobility of the charges increased by 2 to 3 orders magnitude. So we saw that some mobility increase, certainly that you can separate charges very easily, very quickly, right? So in that case, you might increase the efficiency. So that was the initial idea. Oh, so we think, okay, let's try silicon. So go down quite a low temperature. We don't stop at 200 Kelvin. We go further, to just a few tenths of Kelvin. So we found this new results. Okay, so the idea try to distinguish what's the dominant, what the main, determining factors. we apply lasers, a single, surveillance light, at the beginning, and then later we use, so spectrum. So here the setup, so the cell, we didn't produce ourselves. We buy a commercial one, okay? So that no any trick there, no any trick. Just commercial one, here's an N-type, So you can see that the total thickness is about 100 microns in thickness, the cell. And we also test, we apply full type of wavelength light, lasers, like a 450 nanometers, 520 nanometer, 635, and also 980. So these three basically have a common feature. They have the power or the light or photon energy is much higher than silicon bandgap. Okay, silicon bandgap is about 1.12 electrovolts here. So you can see this energy differences compared to the bandgap. So this is a 0.8 electrovolts, 1.2, 1.6. And we also have, so relatively just about the bandgap. So apply this infrared light as a 980 nanometer. So this one just about, so you can still trigger this generation. Okay. So that is, so you can generate this, photovoltaic effect, but not much energy left in this photons. So we has light absorption. You can see all about 90%. So this is the lowest, but still, 93.5%. Light absorption is one of the factors we have to control. And here just has is reverse, forward. So how these cells work or not. So work perfectly. We look at both at the room temperature and the 50 Kelvin. So you can see 50 Kelvin. So this the curve looks really nice, right? It's really nice. You can easily think it's like a few factors are much higher compared to 300 Kelvins. And we also did this in dark room, so look at so the curve very typical. Okay, so we make sure everything is fine, and we test. So like this open circuit voltage, it's open circuit voltage, and the current density, and field factor, and then we calculate this power conversion efficiency, PC. Okay. So you can see here, there's a kind of turning point pretty much here. For this, as mentioned, we use a 520 nanometer laser. Okay, so this turning point pretty much that actually is the highest atmosphere power generated at that temperature. That's a 50 Kelvin. Okay, so if you just simply compare this, the measurement at the room temperature is 300 Kelvin and the 50 Kelvin, so you see this efficiency increased by 2.5 times. So typically that's, the cell that we measure, so use this a single laser, so it's about 22%. And once we down to the 50 Kelvin, we got 56% increase. Okay, no any report before. Okay, so that is a kind of utmost highest energy efficiency at that point. You can see here, decrease temperatures kind of increase, and then that point and decrease again. So it's kind of optimal, it's power generation at 50 Kelvin. We tried, this one for 520 nanometers laser. We also tried 4050 and the 635. Both of them have similar performance, but the only change is it's, the highest output is a shift a little bit. It's like a 450 nanometer laser. So the highest temperature is 52 Kelvin, and for this 635, so the highest the output is so 44 kelvin. Okay. And here that's all. That's that's mobility, as I mentioned. That's you increase a lot. So that and also the density. Sorry, the charge density. Here the energy density charges are not just thermally generated; they are photo generated charge. So photo generated charge are totally different from thermal generated. Okay, so that is a big difference. Because that can avoid this, so-called freezing effect. And from this, mobility, relation with the temperature, you can see they kind of follows a very, straight line here, indicate the mobility as function of temperature with the powers minus 302. So what that means is, this indication of all the, irradiations of this acoustic mode. They do translate to phonons, okay? And however, so basically the phonon numbers can be calculated, and if approaching 0 Kelvin, basically the phonon numbers also become 0. So as I mentioned before, that if you dramatically decrease thermal energy, phonons is thermal based, it's acoustic. So in that case, basically there's no phonon existed at the time. So assuming most of energy transferred to electricity, consider everything others are okay. So this is the message. And however, we also test this low energy photons, as I mentioned, this infrared light, and that behavior a little bit different from this all other three, high energy photons. Okay, so other three here is a kind of decrease temperature, increase efficiency, and coming down. So for this 980, you can see this red curve. So basically there's two peaks. So one is about so from 100 to 200, 100 to 200, 150 to 200. So this is exactly what people found before. Okay, so that is nothing but so in this case it's a dopant elements, so it's dominant. Okay, so this is one peak. And also that decrease, people, when they did the experiment, they stop here. Okay, because they see the efficiency decrease. They didn't go further, and there's another peak. Okay, so this one, for this one, that is about 32 Kelvin for this 980 nanometer report. And that's similar to this full spectrum, so AM 1.5 is this curve, and also have a peak at the extremely low temperature, that's about 30 Kelvin. So we test and we got this result, and no one reported this before. And also this, you can see, even AM 1.5, you can reach 50% of efficiency. So this, okay. All right, I forgot to mention that, this is SQ limitation, the room temperature, this is temperature dependent, we calculated, and all this result we have at a different temperature, the highest output power. And you can see here, so open circuit voltage increase dramatically with the increase of mobility. Okay, so that is I think try to avoid this so-called freeze out effect. You have to have the light that can penetrate all through the thickness of this solar cell. Oh, so this is what we learned. I think for the application, just let me go here. So what could be the application, because that has to be applied at the extremely low temperature. Where is the low temperature? So that will be out in the deep space. Okay. So probably, this craters at the moon, right? The South Pole. That this rim is kind of all times under sunshine, but this craters is always dark and at extremely low temperature. And people really found that it's a potential here. They tested hydrogen and means water existed there in the form of ice, maybe. So that's if you try to develop anything on moon, for example, that's you need to have water. That is a must-have. And in this case, I guess the potential that we can apply this technique there. So you have mirrors, you have light there, and you power something like, for example, robots, so astronaut that we wear some like solar cells. They have power. They can do many things. Okay. So because time is run out, I think I will summarize here. Basically, this is the result I just showed you. So we kind of pass this SQ limitation with high potential application in deep and outside space. Thank you for your attention, and I will welcome your question and discussion. Thank you.